evaluate the limit if it exists. And we've got the limit as h approaches 0 of the square root of 49 plus h minus 7 all over h. Now, we can't use direct substitution for a couple of reasons. First of all, that square root doesn't allow it. And secondly, even if it did, we would end up with a 0 in the denominator. So we're going to have to do something to make sure that we don't have a 0 in the denominator. And we've seen a problem like this before, where we had a difference involving a radical. I wonder if you remember what we do in that case. I'm going to rewrite what we have here. So the square root of 49 plus h, and then minus 7 all over h. What we can do is we can multiply the top and bottom by kind of the conjugate of this. Instead of the difference that we have up there, we can multiply it by the sum. So that's going to be the square root of 49 plus h, and then plus 7. And of course, we've got to multiply the top and bottom by the same thing. And when we do that in the numerator, we're going to have something really nice happening. Remember, when we have a difference times a sum, we end up with the difference of two squares, right? If we have a difference, a minus b times a sum, a plus b, we end up with a squared minus b squared. And so basically, what we end up with in the new numerator is that square root squared minus 7 squared. So we've got the square root of 49 plus h squared minus 7 squared all over the denominator, h times that sum. I'm going to leave it just like that because that h is probably going to cancel later, and that's what's going to help us not have a 0 in the denominator anymore. So let's see what this gives us. When you take the square root of something and square it, the square root and the square cancel. And so that's just going to be 49 plus h there. And then minus 7 squared is 49 all over that same denominator. And then you'll notice that 49 minus 49 is 0. And we've got a factor of h in the top and bottom. So if we divide the top and bottom by h, it's going to leave us with 1 in the top, because h is the same as h times 1. And then that h in the bottom is going to go away, and this becomes the limit as h approaches 0 of 1 over the square root of 49 plus h plus 7. And we can't quite use the direct substitution property yet because this is not a polynomial or rational function. We've got that root. But remember, the limit of a quotient is the quotient of the limits. So we can put the limit in the top and bottom. And then the limit of a sum is the sum of the limits. So we can break this up and take these limits individually. And then the limit of a root of something is the same as the root of the limit. So we can pull that limit inside the square root. I'm kind of doing a lot of things at once, but hopefully it's not that scary. So we can write this as the limit as h approaches 0 of 1 over the square root of the limit as h approaches 1 of 49 plus h, and then plus the limit as h approaches 0 of 7. And then once we've done that, we can use direct substitution in all of these situations, and that gives us 1 over the square root of 49, because 49 plus 0 is 49, plus 7. And then we know the square root of 49 is 7, so this is 1 over 7 plus 7, which is 1 over 14. And that is our limit. I know it's a lot of algebra, but it is a little bit nicer than making a table of values, particularly because if we make a table of values and we've got a bunch of decimals, you might not recognize that the limit that the decimal numbers are approaching is 1 over 14. You might just see a bunch of decimals kind of getting smaller and smaller or larger and larger, depending on how it goes, and it might not be clear what that actual limit is. And so this gives us an actual value for the limit instead of some sort of decimal approximation. So there's multiple ways in which this is better than a table of values.